We ended up our last class by doing a thought experiment where I sort of asked you to imagine that you have these extendable go-go gadget style arms that go up to 3 feet in length, right? The question is, how far apart can your hands be? Right? Is there a minimum distance that your hands can be apart from one another? And is there a maximum distance that your hands can be apart from one another? And you said that the answer to both of those questions was yes. That on the one hand, if my arms are 3 feet long, my hands could be 0 distance apart, right? They could both be extended all the way in at my torso, right? On the other hand, there's a maximum, and that the maximum distance that they can be apart is 6 feet, and that's if I extend them all the way out from my torso, right? And it seems like a silly thought experiment, but it really is an example of, really in large part, what analysts, people who study analysis, need to do. Is they have a quantity, in this case it's the distance between my two hands, and they ask the question of themselves, often rhetorically, what control do I have over this quantity? What do I know about this quantity? Even if I don't know what the specific value of this quantity is, I can sort of put it in a box. I can trap it. I can find some bounds for it. That's why we started the semester by talking about bounds. It's a major theme throughout analysis. And in this thought experiment, you convince yourselves that we can bound this quantity from below by 0, and that we can bound this quantity from above by 6 feet, I guess, in this case. And the really interesting part about this is that I feel like this is an easy thing to visualize and conceptualize. But when it comes to actually writing it down using algebra and inequality symbols, that's where some of the meaning tends to get lost. Right? So as we get deeper into the weeds with that stuff this semester, just try and hang on to that intuition that you had during that thought experiment, because I think it'll really help you not to lose sight of where we're going with this. What we want to do today is to take that first step out of the thought experiment and into something that feels like analysis. Because remember, what we're really doing with the absolute value in our class is we're using it as a tool to measure distance. Distance between two real numbers on the number line. That's the sole function of what absolute value is going to do for us in the course. And the central idea behind how we got this 0 and this 6 is an idea that I want to, again, tie back into the triangle inequality. So we finished our last class by asking, where did this number 6 come from? From the information in the problem, we knew that each of our arms was 3 feet long. So 3 was actually the upper bound. But 3 was the upper bound on what distance? Not the distance between left hand and right hand, but what is 3 the upper bound for in this problem? Distance between what and what? Yeah, the 3 in this problem is actually an upper bound on the distance between either of these two hands and your torso in the middle, right? So there's kind of this third point that's implicit in the statement of this thought experiment. And so what we know in the beginning of the setup of this problem, make a little space here, we know that the distance from left hand to torso is less than or equal to 3, and we know the distance from the right hand to the torso is also less than or equal to 3. So these are the things that we know based on this sentence right there. So we can, what an analyst would say, we can control the distance from L to T, and we can control the distance from R to T. Right? We know that those distances are no more than 3 feet long. Right? So then the question is, how do we take these two distances, which we can control, and say something about this distance, which is something that we don't know offhand that we know how to control, right? The distance between left and right hand. We don't know that we can control that. But we can control the distance between the left hand, the right hand, and this third point. So what the triangle inequality does is it helps us to make that connection. So how do we know we can control the distance from L to R? In the first place, we don't necessarily know, right? If we don't have the triangle inequality in our pockets, maybe we can't control the distance from left hand to right hand. So the triangle inequality is how we bridge that gap. It gives us a way of connecting the control that we have between left and right hand and torso on the one hand, and the distance between left hand and right hand, which is what we really care about. And the way that it looks when you read it in a proof, or when you write it in a proof, as you'll be doing with your groups today, is kind of surprising. We did this right at the end, and so it was Friday at -1 minutes before the end of class. So let me remind you where we were at. What it looks like to apply the triangle inequality to this absolute value of L minus R is not obvious at first. So our triangle inequality exists in two different versions. The first version is the one that we use the most often. It gives us an upper bound, so it gives me a less than or equal to. But what it gives me an upper bound on is not the absolute value of the difference, right? Not really the distance between x and y, but rather it's the absolute value of the sum, absolute value of x plus y. So right there, if we compare this with the inequality that we're trying to get control on, right? So we're trying to get control on L minus R, less than or equal to something. On the one hand, it looks like this isn't a great match for this, because this absolute value has got a plus in the middle, this absolute value has a minus, and so really is a distance. So that's the first clue, that we can't just probably go straight at this using the triangle inequality. We could try and fit a square peg into a round hole and rewrite this a little bit. I'm fond of telling my remedial algebra students, every addition is a subtraction in disguise. Every subtraction is an addition in disguise, right? We can trade one of those for the other. So is there a way that I can rewrite L minus R as a sum instead of a difference?
L, absolute value of L plus negative R.
Yeah, I'll just put an opposite sign on the R, so the additive inverse. So one way of going at it would be to try that trick, right? Turn the subtraction into an addition and then use the triangle inequality to see what it's going to tell us. So what would the triangle inequality tell me if I applied it to this sum? The absolute value of L plus the opposite of R is going to be less than or equal to what? So the triangle inequality tells us that the absolute value of a sum is less than or equal to the sum of the absolute values. Right? And so I would have here the absolute value of L plus the absolute value of the opposite of R on the right-hand side. We could do some simplification on that. What's going to happen to this minus sign right there when the absolute value does its work? Right, it's going to go away, and that's because of this property, property B. Negative R, or rather the opposite of R, is really negative 1 times R. So I could rewrite this as negative 1 times R, and then use property B from right here to take negative 1 times R and the absolute value and turn it into the absolute value of negative 1 times the absolute value of R. And then what's the absolute value of negative 1? It's 1, and 1 times the absolute value of R is just the absolute value of R. So it looks as though we've kind of succeeded in what we set out to do, right? On one hand, is we've applied the triangle inequality to this thing, and we've convinced ourselves that the distance between left hand and right hand is going to be no more than the sum of the absolute value of L and the absolute value of R. And what are those? Those are the distances of L and R to what point? Those are the distances not to the torso, because we don't know where the torso is located, but they're the distances. The absolute value of a number is its distance from 0. So on the one hand, we have got a bound, but it's a bound that re-expresses this in terms of distances from 0. When what we wanted was a way to re-express this bound using let us make use of the information we knew. And the information that we know is not the distances from L and R to 0, but rather the distances of L and R from the torso, which is some other point on the real line. So what we need is a way to use that same triangle inequality that we just used, except instead of ending up with distances from 0 on the right-hand side of it, we want to end up with distances from the torso on the right-hand side of it. So how we do that is we do a nifty little trick that I call the add and subtract trick. We saw this at the end of our last class, but it's worth repeating, and you're going to repeat it in your group several times today. And the trick is to just take the absolute value of L minus R, right, the distance that we care about, and we're just going to sneak in between the L and the R here an addition and a subtraction by T, the position of our torso, right? So we know that we can control the distance between L and T and the distance between R and T, and so this little trick, subtracting and then adding the same quantity, clearly that's going to be the same quantity as the one we started with, right? Because we've just added 0 down here essentially. But the benefit of this is now that I have an addition sign inside of my absolute value. And as soon as I have an addition sign inside of my absolute value, I can invoke the triangle inequality, which says that the absolute value of a sum is less than or equal to the sum of the absolute values. And break apart this absolute value into being less than or equal to the absolute value of L minus T plus the absolute value of T minus R. Right. This is the key step in this whole process. It's this addition and subtraction that happens here, followed by the application of the triangle inequality that happens right there. This is what takes the distance between L and R and reframes them in terms of distances between L and R and T. Just to get a quick picture in here. So L is here, R is here. I want to know something about the distance between these two. I want to be able to control that distance, remember, is another way to say it. And so what we do is we introduce a third party, T, the torso, and we come up with a way that we know we can control the distances from L and R to T. So we know something about this distance, we know something about that distance, and because we know something about two of the distances in this triangle, the triangle inequality can tell us something about the third. That's the whole purpose of the triangle inequality. So this is kind of a schematic diagram, right? Another way to say it would be to just directly make the observation here. We know that this distance is less than 3, less than or equal to 3. We know that this distance is less than or equal to 3. And those two upper bounds, combined with the triangle inequality, will give us an upper bound on the distance that we don't know. So that trick of adding and subtracting t is exactly the trick that we're going to use over and over again. When I have a couple of things I don't know the distance between, but I have something else which I know the distance between. The triangle inequality gets us there. So how this will look when you write it in a proof, or when you read it in a proof, is that I start with this quantity that I want to control, the distance from L to R. And I don't know how to control it off the bat, but if I can rewrite this quantity in a way that lets me use the triangle inequality to split it in terms of two quantities which I do know how to control, then we'll be in good shape. And we do that by subtracting and adding the same quantity inside the absolute value in between my L and my R. So I just wedge that minus t plus t on the inside. And the key reason why that works is that we know how to control the distance from L to T, it's less than or equal to 3, and we know how to control the distance from R to T, it's less than or equal to 3. So these are things that we know. They're given to us. And so then we use the triangle inequality to split this absolute value across this sum. And we end up with a less than or equal to sign. Whoops. And then we'll have absolute value of L minus T plus absolute value of T minus R. So now we've split this big absolute value into the sum of two smaller absolute values. And this one, absolute value of L minus T, we know we directly have control over how big that can be, right? That's got to be less than or equal to 3. So I'm just going to kind of write that underneath just for my own scratch work. That's less than or equal to 3. What about the absolute value of T minus R? What do we know about that? Well, yes, but let's convince ourselves that this absolute value has anything to do with that absolute value. What's the difference between the absolute value of T minus R on the one hand and R minus T on the other? What happens to a difference when you reverse the two summands? 3 minus 6 versus 6 minus 3? They're equal and opposite, right? They have opposite signs but have otherwise the same absolute value. If we want to convince ourselves of that, just factor out a negative 1 from the T minus R quantity. So just to be really brutal about this, we start with T minus R. If I factor out a negative 1, I'm going to get minus T plus R, right? But then minus T plus R is just another name if we rearrange the summands as R minus T. But this negative 1 multiplying inside the absolute value for the same reason that it disappeared before, because of property B, it's going to disappear again. When I break this apart across multiplication, absolute value of negative 1 is going to go away. It could become 1. And then I'm going to get just the absolute value of R minus T. So yes, those two things are the same. This is also true if we believe that absolute value satisfies the properties, the axioms of a norm, a metric that we talked about last time. And one of those properties is symmetry. The distance between x and y is the same as the distance between y and x. And so that's the reason why that property holds for absolute value. And now we can use what we know about the distance between r and t, that we have an upper bound on it, it's less than or equal to 3. And therefore, this is less than or equal to 3, that's less than or equal to 3, and so we can conclude that this whole thing is less than or equal to 3 plus 3, which is 6. So if we were writing a proof of your assertion at the end of the thought experiment, this is how the proof would likely look. So one more time quickly from beginning to end. We want to find an upper bound for the distance from L to R. We don't know how to do that, but we do know how to bound the distances from L and R to T. So we'll add and subtract T in the middle of my absolute value, which doesn't change the quantity. But it does give us the opportunity to use the triangle inequality to split the absolute value of a sum to be less than or equal to the sum of the absolute values. And after switching the order of the T and R, we find out that each of these two distances is something which we do have an upper bound for, and therefore this sum is going to be less than or equal to 3 plus 3, which is 6.